We will now explore performing operations on functions. So think about this. A function, for an input, we get a certain output that is a real number, and we can add, subtract, multiply, and divide real numbers. Therefore, we can add, subtract, multiply, and divide functions. So we will define operations of functions in this way. If f and g are functions, and x is in the domain of f and g, then we define the sum of functions, f plus g of x, to be f of x plus g of x. The difference of functions, f minus g of x, is f of x minus g of x. The product of functions, f times g of x, is equal to f of x times g of x. And the quotient of functions, f over g of x, is equal to f of x divided by g of x, for g of x not equal to 0. For the domain of these operations, the domain of the sum, difference, and product of f and g is a set of real numbers in the intersection of the domain of f and the domain of g. Intersection means that it is the set of numbers in both of those domains, so that it is the common elements. For the quotient, we have to have one additional requirement, and that is we have to exclude the values of x for which the denominator, g, is equal to 0 if we're talking about the quotient of f divided by g. So let's look at how we apply this. In this example, we have f of x is equal to 3x plus 2, and g of x is equal to x plus 5. We want to find the indicated function or function value and state the domain of the combined function for parts A through D. Part A is the sum of two functions, f plus g of x. So by the definition that we just stated, this is equal to f of x plus g of x. So to find the sum, we will add the 3x plus 2 to the x plus 5. So we literally just add the two expressions together. Combining like terms, we get 4x plus 7. Now we're asked to state the domain of the combined function. Well, we have to look at what is the domain of f, and I'm going to write this as a d with a subscript of f. Remember that f is a linear function. The domain of all polynomial functions is all real numbers, so we know the domain of f is negative infinity to infinity. To do the domain of g, well, that is also all real numbers since this is a linear function. So if the domain of f and the domain of g is all real numbers, then the domain of their sum, f plus g, which is the intersection of these two domains, is also all real numbers. Part B is f minus g of x, so the difference of functions. This is defined to be f of x minus g of x. So f of x is 3x plus 2 minus, be careful here, we have to subtract off everything that is part of the function g, so we put in parentheses x plus 5. Therefore, we get 3x plus 2 minus x minus 5. Combining like terms, we get 2x minus 3. Now again, because the difference of function has the domain of the intersection of the domain of f and the domain of g, it turns out that the domain of f minus g is also negative infinity to infinity. Part C is to find f times g of x for these two functions. So this is f of x times g of x, which will be in parentheses 3x plus 2 times in parentheses x plus 5. And we can distribute to get 3x squared plus 15x plus 2x is plus 17x and plus 10. Now again, the domain of the product is the intersection of the domain of f and g. We just saw in the last slide that the domain of f and g are both all real numbers. Therefore, the domain of f times g is also all real numbers. Part D is to find the quotient f divided by g of x. This is equal to f of x divided by g of x, which is 3x plus 2 divided by x plus 5. So the domain of f divided by g is the intersection of the domain of f and g, excluding any values that make the denominator 0. So we know that x plus 5 is equal to 0 at x equals negative 5. So if we think about all real numbers except for negative 5, we will have negative infinity to negative 5, parentheses, union, parentheses, negative 5 to infinity. And then part E and F are to find specific function values. It is still f of x is equal to 3x plus 2 and g of x is equal to x plus 5. And we are asked to find f plus g of negative 3. So giving a specific value for x, we can find f of negative 3 plus g of negative 3. And f of negative 3, remember we replace the x value with negative 3, so this would be 3 times negative 3 plus 2, that is our f of negative 3, plus g of negative 3, we plug negative 3 into x in place of this function g, so we would get negative 3 plus 5. So this is negative 9 plus 2 plus negative 3 plus 5, or what is that, negative 7 plus negative 3 is negative 10 plus 5 is negative 5. Now an alternate method would be to actually find f plus g of x, which we found that in the first example. Let's review this. We found that f plus g of x is 4x plus 7. So we could say that f plus g of x is 4x plus 7. So then if we wanted to find f plus g of negative 3, it would be to plug negative 3 into this sum function. 4 times negative 3 plus 7 is negative 12 plus 7, which is negative 5. So either way would be appropriate. And then part F is to find f minus g of 5, which we define to be f of 5 minus g of 5, which we could then replace x with 5 in each of the functions and subtract them. That would give us 3 times 5 plus 2 is f of 5. And then minus g of 5 would be 5 plus 5. So we would get 15 plus 2 or 17 minus 10, which is 7. Or alternatively, we can look at what did we define for f minus g of x, and that was 2x minus 3. So f minus g of 5 could also be found by plugging in 5 into this difference to be 2 times 5 minus 3, which is 10 minus 3, or 7. We'll do 2 more examples using functions. We have f of x is equal to the square root of x plus 3, and g of x is equal to 7x. We want to find the indicative function and state its domain. In part A, we have f minus g of x, which is equal to just f of x minus g of x. So we replace f of x with square root of x plus 3 minus g of x. Since it's just a single term, we can just subtract off 7x. Now we have to be careful about the domain of this difference function, because x has to be in both the domain of f and the domain of g. So let's look at this. The domain of f, we have this square root function, and this is only defined when x plus 3 is greater than or equal to 0. So that is when x is greater than or equal to negative 3, which, if you recall, is from negative 3 to infinity. Now the domain of g is where 7x is defined, but that's a linear function which is defined for all real numbers, negative infinity to infinity. So for the domain of f minus g, we have to take the intersection of those two sets. So that means we'll look at where do those two sets overlap. Negative infinity to infinity, I'm just going to draw this as a whole number line, right? And negative 3 to infinity is to the right of the negative 3. So where those two graphs overlap is only from negative 3 to infinity. Right? We have to include what is in both domains. F divided by g of x is defined to be f of x divided by g of x, which is just rewrite these functions in place of the appropriate numerator and denominator. We would have the square root of x plus 3, all divided by 7x. So we take the intersection of those domains, which we just found is negative 3 to infinity, but then we have to exclude where the denominator is equal to 0. So 7x is equal to 0 at x is equal to 0. So think about this. We've got to take the set from negative 3 to infinity, but at 0, we have to exclude it. So we're going to have a hole in our number line at 0. So that means that the domain of f divided by g is going to be from negative 3 with a bracket to 0 parentheses, union parentheses 0 to infinity. So again, that came from the intersection of the domain of f with the domain of g minus the value that made the denominator 0. Now part C is g divided by f of x. We apply the same definition, which is g of x divided by f of x, which written out is 7x divided by the square root of x plus 3. So we have to again find the domain of g divided by f. So think about it like this. It is the negative 3 to infinity, that's the intersection, minus the value that makes the denominator 0. Well, the denominator, square root of x plus 3, is equal to 0. We could square both sides to get x plus 3 is equal to 0, or at x is equal to negative 3. So we have to take this set from negative 3 to infinity, but we have to take out the endpoint of negative 3, so instead of including it, we're going to exclude it. So the domain would be from parentheses negative 3 to infinity. Now we want to let f of x equal 1 divided by x plus 3, and g of x is equal to 1 divided by x plus 2. And here we're just going to look at what is the sum of the two functions, and we want to state its domain. So f plus g of x is equal to 1 divided by x minus 3 plus g of x, which is 1 over x plus 2. So I should have written that out here, f of x plus g of x. Now to add fractions, do you remember you have to get a common denominator? And the common denominator here is x times x minus 3. And then we need to rewrite each expression with that as its denominator. And to do this, to go from 1 over x minus 3 to a denominator of x times x minus 3, we need a factor of x. And remember that to do this, you have to multiply the numerator and denominator by the same expression, so that you're multiplying by 1, which does not change the value of the fraction. This becomes, therefore, x divided by x times x minus 3. To go from 1 over x to a denominator of x times x minus 3, we need the factor of x minus 3. So we have in the numerator just 1 times x minus 3, or x minus 3. And then the 2, remember that it is really 2 divided by 1. So to go to this LCD, we are missing both the x and the x minus 3 from the denominator. So we need to multiply the numerator and denominator by the x times x minus 3. And therefore we get 2x times x minus 3, which when we multiply is 2x squared minus 6x when I distribute by the 2x. Now we have a common denominator of x times x minus 3. So we can add the numerators to have x plus x minus 3 plus 2x squared minus 6x. Therefore we get 2x squared. 2x minus 6x is minus 4x, then minus 3, all over x times x minus 3. That was a lot of work. But now we need to think about the domain. So the domain of f, let's think about that. This is a rational function. The only restriction is where the denominator is equal to 0, so that is where x minus 3 is equal to 0, or where x is equal to 3. So it is all real numbers except for the 3, which is negative infinity, comma 3, parentheses, union 3 to infinity. The domain of g, well, its denominator is x, and so x is equal to 0 at x equals 0, so its domain is negative infinity to 0, union 0 to infinity. And so to find the domain of f plus g, we have to take the intersection of these two sets. So the intersection is all real numbers except for the 0 and the 3. So we would write this as negative infinity to 0, parentheses, union parentheses 0 to 3, close parentheses, union parentheses 3 to infinity. And then one last example that I want to do is now using a graph of the functions to find the sum, difference, and product and things like that. So we have the graphs of y is equal to f of x, which is just a line that goes through negative 2 on the y-axis and 4 on the x-axis. And y is equal to g of x, which is the absolute value function shifted left 1 and down 4. So the vertex of this is at negative 1, negative 4, and it goes through also 0, negative 3, and 3, 0, and also negative 5, 0. We're asked to find f plus g of negative 2. So we do this by applying the definition first. This is equivalent to f of negative 2 plus g of negative 2. Now remember, on the graph, to find f of negative 2 means what is the y value when x is negative 2. So we go to our graph of f, which is the graph in blue. F of negative 2 is, notice at this point, negative 2, negative 3 is on the graph of f. So f of negative 2 is negative 3. Plus g of negative 2, well, the graph of g, which is the red graph, also intersects that point of negative 2, negative 3. So g of negative 2 is also negative 3. So we have negative 3 plus negative 3, or negative 6. Part B is f times g of negative 4. By definition, this is f of negative 4 times g of negative 4. F of negative 4 means what is the y value when x is negative 4 on the function f. So our function f is a blue graph again. So we go to negative 4 on the x. Where does it hit the graph? We'll notice at this point, negative 4 is on the graph of f. So f of negative 4 is negative 4 times g of negative 4. Well, we go to the red graph now. Look at the x value of negative 4. Where does it meet our graph g? And that is at negative 4, negative 1. So g of negative 4 is negative 1. When we multiply these two y values, negative 4 times negative 1, we just simply get 4. Then we have f divided by g of 0. By definition, this is f of 0 divided by g of 0. So f of 0, that is our blue graph. Notice that the x value of 0, the y value is negative 2. So f of 0 is negative 2. Divided by g of 0, well, the point 0, negative 3 is on the graph of g. So g of 0 is negative 3. Therefore, negative 2 divided by negative 3 is a positive 2/3.